Hello everyone, I am Dr. Nehal Shah. In this video, we are going to study how to measure rise time, fall time and propagation delay for CMOS inverter. Here in this diagram, schematic of CMOS inverter is shown. We can perform spice simulation using LTSpice and schematic can be drawn in electric. For working with electric and LTSpice, video link is given over here. You can also see the video for implementing CMOS inverter using electric and LTSpice. At the end of second video, you are able to verify logic functionality of CMOS inverter. In this video, we are going to measure rise time, fall time and propagation delay for CMOS inverter. For that, we are going to change W by L ratio of NMOS as well as PMOS transistor. We will also observe effect on delay if width of only PMOS will increase as well as effect on delay if width of both the transistor will increase. Also note down that rise time will be measured when output reaches from 10% to 90% of maximum value. We will consider maximum value of voltage as VDD. We will also measure fall time when output reaches from 90% to 10% of maximum value. By taking average of rise time and fall time, we can identify propagation delay, or we can use delay time definitions. In this diagram, in first figure, you can observe idealized step input in pink color. The blue color is step input, but that is practical one with some rise time as well as some fall time. On y-axis, you can observe VOL, that is logic low voltage, VOH, that is logic high voltage, and V50%, that is when input reaches at 50%. Look at the third diagram in which you can observe V10% to V90%, that is output reaches from 10 to 90%, and at that time how signal is changing with time, that is being shown. So TA is a time when output reaches to 90%. TB is a time when output reaches to 10%. So TB minus TA will give fall time. Similarly, TD minus TC will give rise time. So in comparison to our input voltage, output voltage is shown over here, and similar kind of simulation waveform we can observe and we can measure rise and fall time. Actual notation of VOL and VOH we will study later. We will also study TPHL and TPLH later. Delay time definitions are given over here just for your reference. Now there are two methods of changing size of inverter. So first method is in electric itself, you can click any specific transistor, do right click and you can change width or length of the transistor. After that, go into tools, simulation and write spice deck. So with specific W by L ratio of NMOS and PMOS, you can write your spice deck. So for a various W by L ratio, just write down few different spice deck which you can simulate in LTSpice and you can measure required parameters. Over here in inverter 1, I have taken W by L ratio of NMOS is 8 by 2 and W by L ratio of PMOS is 16/2. So you can observe for my NMOS, L is 0.4 micrometer and W is 1.6 micrometer. Similarly, for PMOS, L is 0.4 micrometer and W is 3.2 micrometer. We have used scale as 200 nanometer. That's why any unit length that will be multiplied by 0.2 micrometer. You can also observe my second spice stack, that is inverter 2. This is considered for W by L of NMOS as 8/2 and W by L of PMOS as 20/2. That means only for PMOS W by L is changed. So you can observe for my PMOS W by L, that is L is 0.4 micrometer and W is 4 micrometer. Now I am ready to perform spice simulation. So just I'll consider my inverter 1. I'll add required pulse input and transient analysis. And my VDD is taken from VDD to ground, that is 1.8 volt. If I perform simulation, I can observe my input voltage in green color and output voltage in blue color. I can separate these two waveform and I can observe them separately. Manually, I can measure rise time, but that won't be accurate. So, I will add certain lines in my spice stack for measuring rise time and fall time. So, my script will start with .meas, that is dot measure. In my transient analysis, first of all, I'll measure T1 on VB. VB over here is my output, because in my inverter notation, I have taken A as my input and B as my output. So I'll measure T1 on VB when VB will be 0.18 volt. That is 0.18 volt is nothing but 10% of my VDD. My VDD is 1.8 volt. So 10% of VDD is 0.18 volt and 90% of VDD is 1.62 volt. I'll also measure this T1 on my first rise. That's why rise equals to 1 is mentioned. I'll also measure my T2 on VB when VB is 90%. T1 and T2 both are measured on first rise. I can calculate my rise time by using T2 minus T1. Similarly, I'll measure my fall time, that is T3 minus T4. For that, I'll consider fall 1. I'll measure T3 on first fall at 10% and T4 on my first fall at 90%. The difference between T3 minus T4 will give me my fall time. Once I'll execute this, after running my script, I can go into view and I can observe spice error log. So I can observe my T1, T2 rise time, T3, T4 and fall time. You can observe over here that rise time is 2.9 into 10 raised to minus 11 second. So in picosecond I can say it is 29.77 picosecond. Similarly, my fall time observed over here is 14.99 picosecond. So now again I'll take you to LTSpice, and for second inverter I'll show you measurement. The similar lines I'll add after my transient analysis and I'll run my simulation. So you can observe this simulation that was for 3 cycles, but the running time is still 10 nanosecond. We will observe spice error log and we can observe our rise time over here as 27.38 picosecond and fault time as 17.28 picosecond. That means our measurements are changing when we change W by L ratio of our inverter. So, as per table, now use different W by L ratio for NMOS and PMOS and complete that exercise. And after that, note down your observation that what will happen that only width of PMOS transistor will change and what will happen if width of both the transistor will change. Afterwards, once your measurements are ready, we can discuss that in our next video. Thank you very much.